Simple ideas about IIR filters. Low-pass IIR. The fractional form of the transfer function has the same form as the FIR, which contains zeros in pi to remove the high-frequency component. Also, it has a pole in the denominator in the right half and near the unit circle. Okay. H of z is equal to 1 minus alpha over 2 times 1 plus z minus 1 over 1 minus alpha times z minus 1. Here you see the term 1 plus z minus 1 is similar to FIR part, and that's the truth. Anyhow, h of omega is equal to half 1 minus alpha times 1 plus e to the power of minus j omega over 1 minus alpha times e to the power of minus j omega exponential form. Okay. Poles and zeros of low-pass IIR. You see here the same location for zero happen for low-pass FIR, but the pole of FIR from origin has moved to, here say it, 0.9. Inside the unit circle, it cannot be over it or beyond it due to causal stable systems. We have already defined it. Okay. Figures illustrate the poles and zeros and also frequency response of the low-pass IIR filter presented in equation 5.13 respectively, where alpha is assumed to be equal to 0.9. Okay, you see here the form of low-pass filtering for IIR, a very better shape compared to FIR frequency response. Okay, very sharp transition region, very low cutoff frequency, but the price is that the phase is nonlinear. Later you will be more familiar with it. Now, take home 5.7. A program in Python is required to depict all necessary discussions. Now, what about the high pass in IIR design? The fractional form of the transfer function has the same form as the FIR, which contains zeros in zero to remove the high frequency component, the low frequency component, a typing mistake, a copy and paste problem. Also, it has a pole in the denominator in the left half and near the unit circle. The form will be h of z is equal to 1 minus alpha over 2 times 1 minus z to the power of minus 1 over 1, this time plus, not minus, plus alpha times z minus 1, or h of omega is equal to half 1 minus alpha times 1 minus e to the power of minus j omega over 1 plus alpha times e to the power of minus j omega. Here you see the 0 has moved to the z equals to 1, right hand side, 0 degree, and the pole has moved left half part. Okay? This figure and the next one illustrate the poles and zeros and also frequency response of the high-pass IIR filter presented in equation 5.14 respectively, where alpha is assumed to be 0.9. Here you see the idea of high-pass filter. Okay, low frequencies cannot pass, so it's high-pass filter here starting from 500 half fs. Okay. Now, bandpass IAR, the same scenario and the same strategy will lead to h of z be equal to half 1 minus alpha times 1 minus z minus 2 over 1 minus beta times 1 plus alpha times z minus 1 plus alpha to the power of 2 times z minus 2. And I don't want to read the frequency response. You see everything in clear. Okay. Here you see two zeros located at 0 and pi or 100 degree, 180 degree. Okay. Preventing low and high frequencies to pass, but providing middle range frequency to pass. Up to now, you have learned that zeros prevent passing the frequency components related to them, but poles provide facilities for passing. Okay? Figures 5.16 and 17 illustrate the poles and zeros and also frequency response of the bandpass IIR filter presented in equation 5.50 respectively, where alpha is assumed to be 0.9 again and beta be equal to 0.6. Here you see frequency response of bandpass filter. Middle range frequencies have passed, but no permission for low and high frequencies. Okay. What about band stop IIR filter? Similar idea. 1 plus alpha over 2 times 1 minus 2 beta times z minus 1, here missing part, typing mistake, plus z to the power of minus 2 over 1 minus beta times 1 plus alpha times z minus 1 plus alpha to the power of 2 times z minus 2. No need to repeat for h of omega. Okay. Two zeros to prevent the pass of the middle range frequencies, and we have located two poles near it to have a better shaping for band stop. Okay, alpha is equal to 0.9 again, and beta is similarly 0.6. Here you see that the middle range frequencies have no right to pass, so it's band stop. Okay, stopping middle range frequencies to pass. Right. What about all pass IIR filter? A very important topic. Okay, just look at the denominator 1, D1, D2 up to Dn. If you flip their locations and put it here, it will be all pass IIR. Okay? Flipped version of what you see here will appear in the numerator. It's inferred that the coefficients of the numerator is a flipped version of those in denominator. Okay. Here, for a given example, you see the location of poles. Okay. 3 poles inside the unit circle and 3 zeros anywhere. There is no restrictions or limitation for zeros up to here. Later we'll have some idea about the location of zeros, but not for now. Okay? Figures 5.20 and 21 illustrate the poles and zeros and also frequency response of the all-pass IIR filter presented in equation 5.70 respectively, where the degree n is equal to 3. Okay. Here you see the amplitude or magnitude is always 1. Permission granted for all frequencies up to end, which is 500 when sampling frequency is 1000 Hz. And here you see the idea about the phase.